I feared, your test for this unit is going to include information that we didn't get to cover in class, and that's partly because we didn't get to do a full week on mitosis and a full week on cell division and the cell cycle, and a full week on enzymes. So I'm going to go over a few things that will be on your test, and hopefully you'll watch this and get caught up with your study guide. And if you have any questions, please email or ask so I can get you where you need to be. So I'm going to be looking at my computer as well as doing this at the same time. One of your questions is, what is the role of cyclin or CDK in the cell cycle? Well, a cyclin is, let me pull this up so I make sure I tell you correctly. Cyclins are parts of your cell. They're enzymes in your cell, and the cyclins are what kind of helps to control the cell cycle doing its job. So if you look it up online, it simply says cyclins drive the events of the cell cycle by partnering with a family of enzymes called cyclin-dependent kinases, or CDKs. So if a cyclin by itself, or a cyclin is by itself, it won't do anything, but then the cyclin, once it partners with the CDK or the cyclin-dependent enzyme, those make a bond, and then those will be active and drive the cell cycle. So it will either tell it to begin mitosis or to go into the synthesis stage of interphase. But whatever's going on, it'll happen because the cyclin bonds with the CDK, it bonds with that enzyme, and causes the cell to go into the next stage of the cell cycle, or to stop the cell cycle and go into apoptosis, which is programmed cell death. Another one of your questions is, using the gas pedal analogy, explain the impact on the cell cycle of proto-oncogene versus an oncogene. Well, we didn't really get into that too much, but an oncogene is a cancer-causing gene. A proto-oncogene is not a cancer-causing gene. A proto-oncogene will control the cell cycle in a normal, calm fashion. Everything will go as planned with normal timing, but an oncogene is like pushing the gas pedal on the cell cycle, so it causes the cycle itself to speed up and go more quickly, and therefore you're not spending a lot of time in interphase. You're basically just reproducing, growing enough, synthesizing to reproduce again, and you just speed up the cell cycle a lot with the oncogene. So the oncogene is like the gas pedal speeding up the cell cycle. In comparison to that, in the brake pedal analogy, it says, explain the impact on the cell cycle of one mutilated tumor suppressor gene allele versus two mutilated tumor gene suppressor alleles. Well, most of the time these gene suppressor alleles are recessive, so you need two of them in order to, or two of them to be mutated in order to not function properly, though the mutations are recessive, I should say. So a gene suppressor allele, a tumor gene suppressor allele, does just that. It suppresses the tumor that's causing the cancer. So it causes the tumor to go on stop. So if you have one of those gene suppressor alleles mutated, it's like if one of your brakes goes down in your car, it's still going to stop it. It might not be as efficient, but it's still going to be able to put a halt to the car, so the tumor would not grow. But if both of them would be mutated, then the tumor would grow because you don't have any brakes anymore. So you have nothing to stop that tumor or suppress it from growing. One of the questions, it asks you to label a graph about enzymes, and it's when the enzyme has different inhibitors, whether it's a competitive inhibitor or a non-competitive inhibitor. So I'm going to actually turn my camera around to my computer. This is the study guide question that's asking you to label this graph right here, and you'll have this on your study guide. And so if you go to Khan Academy, I really like Khan Academy. It's very helpful sometimes. So I just Googled, I found the graph, and I went to Khan Academy, and it takes you to this basics of enzyme kinetics graphs, and it walks you through what's going on. So in a normal reaction, the rate of reaction is on your side. The amount of substrate, or what that enzyme is reacting with, is on the x-axis. And as you increase the amount of stuff the enzyme is reacting with, the amount of substrates, then the rate of reaction will increase until it levels off. So this leveling off is basically the enzyme is working as fast as it can be. Before this, the enzyme is kind of waiting on the next substrate to be made and available, but once you have plenty of substrate, it can only go as fast as the enzymes can make the reaction happen. You have a question asking about this Km later on in your study guide. And the Km is basically the enzyme's affinity for that substrate. So how easily is the enzyme going to bond with the substrate? You could have a high Km, meaning the enzyme won't bond very easily, or a low Km, meaning the enzyme will bond very easily to its substrate. But Km is half of Vmax. A lot of words I'm throwing at you. Vmax is when it's maxed out, when the enzyme and that substrate are bonding as fast as they can and they're making products as fast as they can. It's maxed out. No more substrate being added is going to change that. Half of Vmax is simply when it's going at half speed. And that's what they have voted, the scientists in charge have voted as this Km amount, this enzyme affinity amount. So when it's going at half speed, that is our Km value, or the amount that our enzyme will be likely to bond to our substrate. Oh, and if you're looking at my screen, I just now see when I turned it around, there's a picture of Devin there in my most recent photos from where he was taking the videos for me, and he took a picture of himself, so he gets to be on my YouTube channel now. You have two types of inhibitors that will change this graph. A competitive inhibitor is one that will be bound to the enzyme, so either the competitive inhibitor or the substrate combined, not both, so they're both competing for that active site at the same time. They'll both be present in the cell, and one will bind, and then it'll get off, and then the substrate could bind, and then it would leave, and the competitive inhibitor would bind again. A non-competitive inhibitor, once it binds to the enzyme, it's not going to let go, and it's going to keep that enzyme from being functional anymore. So in your graph, when you're looking at these, your normal enzyme is this top line. Your competitive inhibitor is in green, so eventually it will reach its max, but you've got to have enough substrate to be competing against that inhibitor to keep it from bonding all the time. So it has to level out with the competitive inhibitor. And in the non-competitive inhibitor, once those enzymes are taken up and they can't work anymore, you're never going to reach your max level. It's always going to be a little lower. And if you go on down and read why is this important, it talks about all kinds of different things. But basically, when you're studying enzymes in tissues and how different cells and things work, you want to know how those enzyme levels will be affected in terms of medicine or different things. If you're trying to cause somebody to have a bigger reaction or a lesser reaction to blood pressure or insulin or anything, you can control that with medicines, and so you have to learn to regulate those enzymes in your body. So you could create inhibitors to go in and cause those things to change. So let me go back to my, I know I'm looking around here, back to my study guide and bring it back up and see what the next question was that I knew that we did not really cover. I did talk about structure to function, and anytime with a protein, whatever its structure does determines its job. So if you have pH involved and the pH gets too high, then the structure is going to change because it's going to change its shape, and then it's not going to be able to do the same job that it was able to do before. On this graph, this was the Km question, it asked you to label Km on the graph. Where would it be? So Vmax is, of course, this top line where the reaction levels off, and Km would be half of that point, so it would be about right here where it's half of the max concentration. It's the enzyme efficiency. And then that's about it, so I hope that was